Thank you. Hey, everyone. Hope you had a good long weekend. I want to finish with numerical descriptions of data today. So hopefully we can start on probabilities with probabilities on Thursday. We'll go a little faster today. Remember last time we were talking about measures of center. We talked about the mean value, the average value, and then we spoke about the median as well. And the median was the value that splits the data in half. The median was not affected by outliers. That's the most important feature of the median compared to the mean. Okay? Moving forward, the mean has very important properties for probability theory and statistical theory. So it will be used in more advanced analysis tools. So for example, we measure the spread of data around the mean, not around the median, because the mean has certain properties that allow us to be unbiased in that measurement when we talk about variance later in this class. The third measure of center is called the mode, which is usually not discussed for continuous probability or quantitative data. The mode is very useful for qualitative data, as we will see. The mode, by definition, is the value that occurs the most in a data set. So you have a bunch of numbers, you have a bunch of colors chosen in a box. The mode is simply corresponds to the color or to the data point that occurs the most. It can be used both for qualitative and quantitative data, and we'll see how it looks like. And it will be our choice of measure of center for qualitative data. So, if I give you a box of crayons, like I go pick my kids' box of crayons, what color do they have the most of? It's going to be the mode, but I can't say what's the average color or what's the median color, maybe, right? But you can, because you can't rank those colors, right? You can't rank those data, those pens. So anyway, the mode is very useful for qualitative data. Now, there are some rules. If all the data values occur only once, so then there is no mode. In other words, when you have a uniform distribution, later we will call that a uniform distribution. If you plot the data or the frequency distribution of your data for each quantity, for each value on the x-axis, you only have one value or two value. Everywhere is the same, then there is no mode. If one value occurs more frequently than the others, then we say it's a unimodal data set. If two values occur equal often and more than others, then we say that the data is bimodal. They have to be equal, although sometimes we can even say, when you see some data where you have two peaks to it and the peaks are not equal, we still say that's bimodal, where one mode is higher than the other mode, but you can still call it bimodal. It's okay to say that. If more than two values occur more often than others and they're equal, we say it's multimodal, so trimodal or multimodal. Here's a little example I'm going to give you. We have these sets of numbers. They're unordered. So obviously, the first thing you want to do when you want to look at at unordered data is to order it so you can see which number occurs the most. And so we can go through those one by one. For this first list, you have 1, 2, 4, 5, 6, 7, 7, 7. So 7 is going to be the mode for those data because it occurs the most. It occurs 3 times. 6 is right after it, but it's not going to be a mode. It's just going to peak at 7. So for the other set, we have 1, 3, 4, 6, 7, 8, 9. There is no mode over here because each data point occurs only once, right? So we're counting here the frequency, how many times these numbers occur. So if you think of this as the x-axis, and on the y-axis you're plotting how many times these data occur, there's no mode in this case. For these data, you got 2, 2, 3, 5, 7, 7, 8, 9. There's two modes here. The first mode is 2 and the second mode is 7. Okay, they both occur an equal amount of times, an equal number of times. Okay, and so it's a bimodal distribution. And for the last data set, which I forgot what it was, let me see. You have 2, 2, 3, 3, 4, 4, 5, 5. So how many modes do you think we have in that one? There's no mode. Although they each occur twice, but they all occur the same amount of times, so there's no mode. It's not going to be a uniform distribution. Well, it is going to be a uniform distribution because 2 occurs twice, 3 occurs twice, 4 occurs twice, so they're going to be flat. Okay. All right, so this is another example that I don't have in a spreadsheet, but it's easy to do it in a spreadsheet. You can access the mean, the average or the mean, the median, and the mode directly in your Google Sheets by simply calling average on a cell range or the median on a cell range on a mode on a cell range. Now you might ask, is there a function for multiple modes? Yes. It doesn't.
And only like one number
doesn't. Yeah, it doesn't. Yeah, doesn't depend. So once we start plotting graphs in a second and showing you, the mode is where the peak is always. And then when you have multiple peaks, you could say, you have 2 modes, although they're not equal, so we can get away saying that. But yeah, it doesn't matter the size of the data. Now there's a function there's an option that you can use to get multiple modes. This will give you only the first mode, okay? But if you have 2 or 3 modes, and so you have like 2, 2, 7, 7, 15, 15, etc., you can have that return all the modes for you, but you have to add an argument to it. Okay? Now, what's more important for me here is for you to determine, to know which measure of center you need to choose when you are talking to people about data. There's only one rule. For qualitative data, always use the mode. Qualitative data that's not quantitative, continuous numbers that are categorical, like colors, preferences, ranking, etc. Always use the mode. Okay? Always use the mode to report those data for qualitative data. When it's quantitative, use the mean. That's the preferred measure. Now, if the quantitative data has an outlier, use the median. Okay? So for quantitative data, you always go for the mean first. But if you suspect there's an outlier, then you go for the median. Why? Because the median is not affected by the outliers. I gave you the example of Michael Jordan the other day. So here's some examples. You're collecting the sizes of the shirts of the English Premier League soccer jerseys. You get to the Premier League, however many players there are, you get all their sizes. They're small, medium, large, XL, etc. Right? These are categories. They're qualitative. Then what do you do here? You report the mode. You say, oh, medium is the most people have been, in sizes have been wearing. Salaries for a professional team of baseball players. What do you think? So salaries are quantitative, right? So we're going to hit the mean, right? But this is baseball, so there's famous VIP players, could be making 100 times more than the average player. There's the coach, or there's, so there will be outliers in those data. Agreed? So the mean will be very biased by the outliers. In this case, you'd report the median, okay? Prices of homes in a subdivision of similar homes. So this is one street or subdivision. All homes are similar, right? There's not like your $1 million home and everywhere else it's 300,000, right? All of the homes are of the same quality, the same price. So there's no outliers here. We go for the mean value. Agreed? Professor rankings from student evaluations on a scale of excellent, average to below average. What do you do in this case? It's qualitative data, so we're going to go for the mode. Okay? Okay, this is the side note about Michael Jordan. It was University of North Carolina. They reported unusually high average starting salaries for graduate in their geography program. It turns out that the source of this inflated mean was the inclusion of one famous graduate geography program, Michael Jordan. Right? So although he earned his salary from the NBA, but it's still counted as part of the graduate, and they reported the mean, which really inflated their number. That's just bad use of statistics. Okay, so we're still doing measures of center. We're almost done with those. Now we want to go after graphs, which eventually that's what we will be dealing with when data is at hand, as your colleague Aaron used to say, when data is at hand, plot it to understand, right? You forgot that? So graphs and measures of center. The mode is always the data value. When you look at a graph, the graphs we deal with, not like temperature versus position like we did in numerical methods. The graph we deal with in statistics and probability are usually on the y-axis you have a count, a frequency, or eventually it's going to be a probability of something happening. On the x-axis you have the value that you're looking at. So how many times did this value occur, or how many times did that color was chosen, etc. So the y-axis is almost always a count, a frequency. And so the mode is the data value at which the distribution has its highest peak. Remember, if the y-axis is the count, the mode is giving you the value that is most repeated in the data set. So the peak in the curve is going to correspond to the mode. The median is going to split the data in half. In other words, the area in half. So half of the data are going to be on the left of the median and the other half on the right of it. And finally, the mean of the distribution, if it's a symmetric distribution, it's going to be right in the middle, right next to the median. But if you have an outlier, the mean value is always going to be pulled towards the outlier. If you remember our graphical descriptions of data, we had a symmetrical graph, uniform, obviously, everything is in the middle. A symmetrical graph similar to a uniform distribution, but then we had skewed to the right and skewed to the left. If you have an outlier on the right, then the distribution is skewed to the right. If you have an outlier to the left, then your distribution is going to be skewed to the left. Those will also skew the mean value, the average, in their direction. Okay? So let's take some examples. This is one example, all right? Where is the mean, where's the median, and where's the mode? Okay, let's start with the mode. So again, on the x-axis, there's some quantity, you know, like miles driven to school, okay, on the x-axis. On the y-axis, how many people are driving those miles, okay? So it's a frequency distribution. Okay, what is the mode in this curve? A, agreed, obvious, it's always the peak value, okay? Always the peak value. Where's the mean and the median now? So the median is going to split the data in half, the area in half, and it's kind of hard to see, like, right, because you see here there's like a lot of big area, and here it goes down to zero very slowly. Okay? So B or C, which one is the mean, which one is the median? So there's an outlier on the right. Agreed? And what does the outlier do to the mean? So it's going to pull the mean towards the outlier, right? It's going to pull the mean towards the outlier. So the mean is the value, the average value on the x-axis, remember. And if you put a very large value over here, it's going to move the average towards that large value. Think of this, what if you had salaries here, you know? $1, you know, 1,000, 10,000, you know, $1 million over here, right? It's going to pull the mean value, even if you had one person there, it's going to pull the value to the right. So C is going to be the mean, and B is going to be the median. Okay, so do it by elimination. Mode is easy to get. Then it's always about mean and median. Go after the mean first. The mean is always closer to the outlier. Okay? All right. Now, this summarizes it for you. For a symmetrical distribution, they're all at the same point, right in the middle. Okay? So the mode is here at the peak. The mean is right here at the peak, in the middle, and the median is in the middle. Okay? If you skew to the right, then it's going to move the mean value to the right. It's going to move the median a little bit, but not as far as the mean. Okay? Same thing when it's skewed to the left. The outlier on the left is going to pull the mean towards it, and a little bit for the median. It's still not as affected by the mean. Okay? So compare that to the symmetric one. If you put an outlier, the median is going to move just a little bit, but not as far as the mean value. Okay? So keep this in mind. Okay, great. So we're done now with measures of center. We call those measures of center, like how would you represent the data on average? Think of it this way. Those are measures of center. Mean, the three M's, mean median mode, okay? M3, right? BMW M3, if you're familiar with like racing cars. Okay, yeah. I used to drive one. It's pretty cool. Yep. I'll try to find pictures. That's my family back. Okay, measures of dispersion or spread. So now we've only talked about the centrality of the data, but that's only one aspect of summarizing the data, because the centrality of the data doesn't tell you how much of a spread in the data there is. Okay, I get the average height of students in this class, but I don't know how wide of a range do I have in terms of heights. Okay, so we need some measures of spread of the data. We also call that dispersion of the data. Now, don't confuse that with turbulent dispersion or pollutant dispersion, and those have different meanings in engineering. For statistical, well, it kind of has the same meaning, right? Because dispersion is how things are spread out. So I guess it's the same meaning. So how is the data spread out? What is the spread of the data? The first measure is the range. And it's okay, I like to include it, but it's not the most important measure. But at least the range gives you the difference between the minimum and the maximum value. So what's let's say the average height in this class is 6 feet, but the range, you could have, you could go from 5'7" to 6'5", right? So the range is going to be 6'5" minus 5'7", and you get that range of data, how much there is spread in the data. If there's not much spread in the data, then the range is going to be close to 0, right? Because all the data is going to be clustered around the mean. Now, the variability in the data is a very important thing. And the range doesn't really describe how much variability there is in the data. There is a much better measure to describe in the data. You've probably heard of it. You've heard of standard deviation and variance. So we're going to redefine it here and talk about it a little bit more. Now, one thing to observe is that the dispersion, and I'm going to read right off the script here, that the dispersion of a set of data is small if the values are closely bunched together, because then the range, right, there's not much range. All the data are close to each other, close to the mean value. And the spread is large when the values are scattered widely about the mean. We always come back to the mean because it's a very important reference point for the data, for all data. Now, it would seem reasonable, therefore, to measure the variation of data in terms of how far they are off from the mean. If we're always using the mean as our reference point in the data, now we can go on a philosophical discussion of why we use the mean, not the median. Okay, I'll mention that a little bit later, and maybe make it a homework assignment for why the mean is better than the median. But the mean value is always a reference point. And if you've taken regression, and if you took it with me, we always said if we use the mean value as our gold standard to represent data, then we compare everything to the mean value, because that's the simplest measure we can report about data. So if you take the mean as your reference point and measure variability around the mean, right? So points to the right of the mean, points to the left of the mean, take the distance from the mean, then collectively we can use that to get an average measure of variation in the data. So see how that looks like. So you had a bunch of points, x1, x2, we're calling everything x through xn. Right? So if you have these data points, points scattered around, so in the x-axis you have some independent variable that you're measuring, and you're counting the number of events or people or things that are occurring for those data, right? So your data is spread around, okay? And this is the mean value right here, okay? Now, if you take the distance from each data point with respect to the mean, so you had x1 minus x bar. Remember, for a sample, x bar is the mean. For a population, mu is the mean, so it doesn't matter which one we're using here. And then you take all of those distances together. Then, a reasonable measure would be, how about we just average all of those distances? You take x1 minus the mean value, plus x2 minus the mean value, plus x3 minus the mean value, so on. You take them all and average them to get an average distance from the mean, right? That's what I'm after. I want to measure the spread, and that spread is defined by the average distance from the mean value of all of those data points, okay? So let's go ahead and evaluate this. I want you to grab a pen and paper. Let's do a little exercise together. Show me your math skills. Okay. Take that formula, x1 minus x bar plus x2 minus x bar, and so on, plus xn minus x bar over n. And remember that x bar is equal to the sum of x1 through xn over n. Okay, so you can substitute that up there. And let me know what that formula gives you. We did this exercise last semester, something similar to it. Again, we're trying to measure, a sense of the variation of data in a data set. We chose the mean value as our reference point. We take the distance from each data point to the mean value. That's going to be x1 minus x bar, x2 minus x bar, x3 minus x bar. All of those distances together, if we take the average, that should give us an average distance. Maybe. Okay? But try the math. So if I were you, I would just take x bar and substitute it up there and see what it does. So if you take out the parentheses and then sum up all the quantities that have plus in front of them and keep all the quantities that have negative sign, right? So you'll have x1 plus x2 plus x3, etc., minus x bar minus x bar minus x bar minus x bar n times. So try to use that. So take out the parentheses and you'll see things differently. Combine the x1, x2, x3 together, and then combine the x bars together. Okay. Any progress? So if you were to take x1 plus x2 plus x3 plus all the way to xn, that will give you x1 plus x2 plus x3 plus xn. That's one summation. And then you're going to have minus x bar from the first parentheses, minus x bar from the second one, minus x bar from the third one, all the way to the nth one. So that's n times x bar. Right? So you have summation of all the x's minus n times x bar. But what is x bar? It's summation of all the x's over n. N and n cancel out. You get summation of the x's minus summation of the x's. Will be exactly 0. Exactly 0. Okay? So that's a problem. We can't just take the distances from the mean and average them. That will give you 0. Always. Okay, so we need a better measure. We need a better measure so we don't get 0. Now, the reason you get 0 is because you're changing signs. On the right side, you're getting positive value. On the negative side, you're getting negative values, and they just cancel out. So one way is to take the absolute value. Okay? That's legit. And if you've taken regression with me, you've always asked me this question. Why don't we take the absolute value to define the distance from the mean? That's legitimate. Okay? But that's not the common measure that's used, okay, for defining those distances. And I explain why we don't take the mean value, the absolute value. Instead of taking the absolute value, I want you to think of these distances as if they are elements in a vector. Okay, so the first distance is the first element in a vector, the second distance, the second entry, and so on. And then measure the length of that vector with the Pythagorean formula, right? The size of a vector squared equal to the sum of all its elements squared. Now, when you use a square, you don't have that. You have something similar like the absolute value, but the square is differentiable. It has nice continuous properties. The absolute value cannot be differentiated near 0. So that's problematic because it becomes discontinuous, right? So we prefer to use the square. And instead of averaging the absolute values, we're going to average the square of the distances. So we're still working with those distances, x1 minus the mean, x2 minus the mean. Instead of summing their absolute values, we're going to sum their squares. Okay? Now, we're taking an average. You might think that we're going to use this and divide it by n, but instead we're going to divide it by n minus 1 for a sample. And more about that is going to come through the course. But the point is that for a sample, you already lost 1 degree of freedom to calculate x bar. Remember in the exercise we did last time, we were able to deduce a grade. We were able to deduce a grade from given the mean value from the sample, right? Because the mean all the grades were used to compute the mean value, so you lost a piece of information there. So if you have the mean already using the data, you don't have n degrees of freedom. You only have n minus 1 degrees of freedom. And I always thought this explanation is not very thorough because you need more advanced statistical theory to show that this is what's called an unbiased estimator. We don't even know what that means yet. Okay? But let's take this formula now and accept that this formula is an average distance, of the data. Did you have a question, Gretchen? Oh, you're just stretching out. Okay. So now instead of, we took the summation of the squares of the distances divided by n minus 1, n minus n is the number of data points, total number of data points, okay? And we call that s squared, okay? And that's called the variance. And this is a much better measure of the average spread of the data because absolute values are non-differentiable at 0. These are differentiable at 0. The variance is directly tied into the expected value when we do probability theory, and it's directly connected to the normal distribution. And if we minimize this quantity, we can actually derive the normal distribution, which is central to what we call the central limit theorem, where all distributions tend to have a bell curve. It all comes together very beautifully. Okay? Now you can use the absolute value, and that has a name. It's like the mean variance error, the median variance error, but that's it. It doesn't get you any further. It's not a standard measure. The variance, you have to memorize and know this definition for the variance. It measures the spread of the data. Now, for a population, the variance formula is a little bit different than it is for a sample. In that the distances are the same. You're taking the distance of the data point from the mean, you square it, you sum them up. But here you divide by n minus 1 for a sample. For a distribution, for a population, you're still taking the distance from the mean squared, but you're dividing by n, the total number of people in the population. Okay? Because in this case, the mean value is a property of the population, not something deduced from the sample, like we're doing here with the x bar, so you have a mu here. Anyway, be careful when you're measuring the variance. You have to recognize whether you have a population or a sample. Okay, now, if you commit the mistake, you're still going to be okay. If you put n in the denominator, you're still going to be okay, but you will be biased a little bit. You're not going to have a true value for the sample. You'll be a little bit biased if you put n over here, especially for large numbers in the sample. Notice also the symbols. For a population, we have sigma squared. For a sample, we have s squared. If you don't know if you're dealing with a sample or a population, I always go with a sample, assuming it's a sample, or just go and ask, is this a population or is this a sample? Okay? Again, your population, you can define what your population is. It doesn't have to be all the people on Earth. Okay. So when you calculate the variance, typically we're just going to be doing this in Excel or Python, so we're not too worried about how many significant figures we carry. But if you're doing this by hand, typically you round to one more decimal place than the largest number of decimal places in the data. Sometimes you can skip that if you have financial data, but always get one extra decimal point like we did with the mean value. Okay, here's an example, and I think we have that on Google Sheets. So before I read the example, go on Canvas on the front page. There's a link to copy the Google Sheet with the data that we're going to do today. So go ahead and make a copy of that. And I'll show you how we can get the variance in Google Sheets. So far we know average, median, and mode in Google Sheets, and we'll introduce the variance now. And after that, another measure for spread of the data. Now, one thing to observe is that the dimensions of the variance, or the units of the variance, they're squared in the response variable. So if you're measuring something in inches, then the variance is going to be inches squared. Okay, so pay attention to that. If you're measuring something in kilograms, it's going to be kilograms squared. Okay, and it's going to be in the units of what's on your x-axis. Okay, you're measuring salaries, dollars, whatever. Right? It's going to be in that units or dimension squared. Okay, so Jasmine here has just started driving for Uber. Anyone drive for Uber here? Do Ubering? No? Do you use Uber? Okay. Do you walk to campus? Like, are you mostly biking, driving, bus, I guess? Okay. Drive. Okay. Jasmine here has just started driving for Uber. The number of rides she has given each day for a sample, okay, you immediately know this is a sample, okay? For a sample of 5 consecutive days is listed below in these numbers. So on the first day, she did 3 rides, second day, 2 rides, third day, 5 rides, then 6, then 4 rides. Find the variance for the number of rides that Jasmine has given. So it should be easy. So let's grab our Google Sheet. And I'm going to move this to Preston. So these are taken from the textbook, actually. So this is example 3.2.2. I already put the data here. You could be more descriptive. I didn't bother to do that. So we could do the mean. Oops. No. Okay. So we can do the mean just to show you how we do the mean. Okay. And then you just select. Actually, if I do it here, it will auto-suggest for me. No? Okay. It didn't auto-suggest. What? Average, sorry. Google Sheets is being mean to me. Okay. So the average number of rides is 4. And then here I'm going to do variance. You just simply type a var. Okay. Now, if you're confused about this, you open this and you just kind of look at it. This tells you, calculates the variance based on a sample. So be careful. Now, in Excel, this is called var s, var for sample. And var in Excel is for a population. In Google Sheets, it's the other way around. var is for a sample. So remember that n minus 1 in the denominator. Okay? So be careful because this is a sample. We're going to do this in the denominator, n minus 1 in the denominator. So 2.5, the variance is 2.5 what? What are the dimensions? What are the units? Rides squared. This is in squares, okay? This is in, all these numbers are squared, all right? Now, if you want to do the variance for a population, you have var.p, variance of entire population, okay? So that it divides by n instead of n minus 1. Okay, here we have a sample, so we're dividing by n minus 1. So use the var function. Okay? All right. And you can do it by hand. You do the exercise here by hand. You substitute, etc. You get 2.5 rides squared. Okay. Now, the next step out of the variance, because obviously we want things in the dimensions of the variables we're measuring. We want the variance in terms of rides, not rides squared in terms of dollars or inches, right? So you simply take the square root of the variance. If you take the square root of the variance, you get your result in terms of the dimensions of your system, and we call that the standard deviation. Okay? It's a measure of the spread of the data around the mean. Okay? Now, if you remember how I taught you regression, what was the other wording I used for the standard deviation? The error committed in the data if you use the mean value to represent the data. Okay, the average error committed. Okay, so you can do the standard deviation, and that's simply the square root of the variance. All right, so we can go back here and do standard. Let me find my. Now the standard deviation, there's no difference between well, there's going to be a difference between population and sample, right? If you do STD, okay, it's not helping me here. Give me a suggestion. STD EV, standard deviation. Okay, so you see here standard deviation for a population. You see STD EVP for population. Okay, now I think Google people who designed it, they're smart because most studies are dealing with samples, not populations. So they made the function calls simpler for the default function calls were done for samples, assuming you have a sample. So in this case, we do have a sample, so we just want to use STD-EV, and we're just going to give it the range, and it's 1.58 rides. That's the spread of the data. Okay, on average, her variation, Jasmine's variation. So she did 2.5 rides a day on average, with a variation of 1.6 rides, plus or minus. Some days she did more by 1.5, sometimes she did less by about 1.5 rides. That's how you kind of want to think about it, okay? How the data is spread on average. Okay? Now, if that distance is larger, then on some days she would have done way more rides than on other days. So if the standard deviation is large, you know that the data, there's a lot of spread in the data. If the standard deviation is small, you know all the data is clustered around the mean. Okay? Let's continue. Okay, again, for the rounding rule, you do one more. And there's here a little discussion about the origins of standard deviation in this annoying green that, going to catch your attention. So you can read it at home at the comfort in your Uber ride, for example. You can enjoy it. Maybe only you, Finn, can enjoy reading this in your Uber ride. Everyone else, don't read it if you're driving, or wait until you get home. Okay. Let's see. Okay, so the following is another example. You can do. I'll go through it real quick. You can put it in Google Sheets and do the calculation as well. The following data contains the ages in years of every patient seen by a Dr. Dabbs at his urgent care clinic one afternoon. Calculate the standard deviation of the ages of his patients that afternoon. Okay, so now they didn't tell us here. The number one question you ask, is this a population or a sample? Pardon me? Yeah, it's a population because we're looking at all the patients that afternoon. That's the population we're worried about. That's our population. So we have to use n in the denominator. And then first thing, you compute the mean. And so we represent this by mu. And you have the standard deviation sigma, etc. And then you run through the calculation and you get your answer. You could put this in Google Sheets and you get 15.2 in terms of the standard deviation. So his mean number of patients, so let's look at the numbers again one more time. The ages in years, an 11-year-old kid, 18-year-old, 25, 51, 44. So, on average, like there's no demographic he's dealing with, almost a pediatrician here, adult, couple of kind of young adults here, and then mostly middle age and older people. So the mean age he saw was 34 years, okay, out of the 12 patients, and with a spread of 15.2 years. So, you know, some patients were 15 years older than 34, and some on average were 15 years younger, okay? That's how you think about it. There's more, but on average, it's 15 years on average, okay? Again, you can read those on your own. There's other examples also from the textbook as well, but with a little bit more explanation over here. Okay, so other measures now, we're measuring spreads. We looked at the range, then we looked at the variance and standard deviation. Okay, and there's at the end of the chapter, there's a really nice summary of all of those things. Keep them in mind. What's more important is the meaning of those things. Okay, how do you interpret those? Now, the coefficient of variation, it's a measure of the relative variability of a data set, and it describes the spread of the data relative to its mean. So it's like the standard deviation, but essentially it's expressed in terms of the mean value. And it's defined as a percentage. So you take the standard deviation and you divide it by the mean, and you multiply by 100%. So you're going to get a fraction, and you report that as a percentage, whether for a population or for a sample, it's the same thing. You take the standard deviation, either for the sample or the population, and divide it by the mean. Multiply by 100% gives you a percentage, right? And that gives you the coefficient of variation. Now, the coefficient of variation is a nice summary when you're comparing two data sets, because two data sets could have different means, okay? Like you're comparing two classes. They could have two classrooms by two teachers. They could have different means and different standard deviations. So it's not enough to say, oh, the standard deviation in Professor Saad's class is like 50 points, but in, you know, Professor Dab's class, it's 10 points. Well, what about his mean and my mean value? Well, what if my mean is 80 and his mean is 30, right? How do you compare those two values? The coefficient variation gives you that ability to try to compare. That's one way to compare data together. So, and even data that is very different than each other. So here's some data where this is measuring rainfall in inches, okay, and how much you get rainfall with this, however many inches, how many days a year. And so the mean is 26 inches, and the standard deviation is 7.55 inches. Now the coefficient of variation, okay, don't confuse that with the coefficient of determination from regression. Coefficient of variation is 29%. So you're going to take the standard deviation and divide it by the mean value. Now, when you think about that, this is saying that the standard deviation is 28% times the mean value, right? Because it's S over X bar over the mean value equal 28%. Right? So S is equal to 28% times the mean value. So my standard deviation is about 28% of the mean value. Okay? Now, another data set here in price per dollars for 20 acres and how many people are buying this. You got 117,000 for the mean and 42,000 for standard deviation. But like you can't compare these two, right? Because they might be wildly different. But this data, you could say, has a higher coefficient of variation because it's 37%. Here, the coefficient of variation is 29%. So you could say that this data, although they have nothing to do with each other, but this data set is more spread than this data set. Agreed? Just by looking at $42,000 here and 7.55 inches, I can't tell which graph has more spread in the data. When I look at the coefficient of variation, the higher the coefficient of variation, the higher the spread. Okay? So it normalizes things so that you can compare. Like looking at those two graphs, I mean, yeah, I could probably say there's more variation in that one, but it's hard, right? It's not accurate to say it. So when you look at the coefficient of variation, you could quantitatively say that these data are spread a little bit wider than these data, okay? All right, so next we're going to look at what we call the empirical rule for bell-shaped distribution. So now we know standard deviation and variance and range, etc. We're building up to something. Okay, the next thing we're going to look at, and we will derive this later, analytically. But now, remember, we're just looking at descriptive statistics. You're given data. How do you describe those data? Turns out so you've always heard of the bell curve. It's like that nice symmetric curve. Looks like a bell shape. It's called the normal distribution. But that bell curve, when data looks like the bell curve, you can infer a lot of things about those data very quickly without even doing any fancy analysis. And I'll summarize it with this graph. So for data that looks like this, it doesn't have to be exactly like this. Could be a little skewed to the left or to the right, but this is a pretty darn good approximation. So you know the mean value, median, and mode, they all sit here in the middle. You are guaranteed that 68.3% of the data lie within one standard deviation from the mean. Okay, so plus one standard deviation, minus one standard deviation. And then 95.5% of the data lie within two standard deviations of the mean. And then 99.7% of the data lie within three standard deviations of the mean. So you can say a lot of things from this empirical rule. It's actually not empirical because you can derive this analytically for the normal distribution. But we use it empirically when we have data that looks like it's bell-shaped. Now, this is super helpful because if I'm given data, all I need to know is the mean and the standard deviation. And then I can say all sorts of things about how the population is distributed on those data. Okay? And I'll show you in the example. So remember this, 68% of the values are within one standard deviation of the mean only for bell curves. Only for bell curves. If it's too skewed to the left, to the right, if it has two modes in it, forget it. Only for bell curves, and they're predominantly available. Like you'll see that a lot of data you'll collect, they look like bell curves. And surprisingly, for when you're looking at human statistics like weights, heights, the head diameters, etc., you'll find that the bell curve shows up all the time. And there's a natural tendency for nature to go to the bell curve. Okay, so 68% of the data is within one standard deviation. 95.5% is within two, or 95%, and 99% is within three standard deviations. Okay, so another way I'm writing it here, I'm using mu for the mean of the population, then mu plus sigma, mu minus sigma, right? That's plus one standard deviation, minus one standard deviation, and so on. Okay, here's an example that will anchor how we're going to use this in your mind. The distribution of weights of newborn babies in one region is bell-shaped. So we know in Utah here at Clinic 6, if you have kids, you probably go to Clinic 6 at the university or Wasatch Pediatrics. And you look at all sorts of charts. They measure your baby and like they weigh them. And I always criticize their measurements because they're like, you know, the kids are, you know, they're like bending, etc. I'm like, no, you need to stretch them out a little bit, measure from head to toe so you get an accurate measurement. Anyway, I had to teach sometimes the nurses about that, but anyway, but then they report to you all sorts of stats. Oh, your kid is 50th percentile and whatever. So what does that mean? We're going to learn that today. Okay? So the distribution of weights of newborn babies in one region is bell-shaped with a mean of 3 kilograms or 3,000 grams. So the average weight of a newborn baby in this region is 3 kilograms and a standard deviation of 500 grams. So on average, the spread of those babies, their weights, is 500 grams, and the data looks like it's bell-shaped. Now they ask us, what percentage of newborn babies weigh between 2 kilograms and 4 kilograms? Okay, so how many of those babies weigh between 2 and 4 kilograms? And what percentage weigh less than 3,500 grams? Okay, and then calculate the range of birth weights that would contain the middle 68% of baby weights. Okay. So let's do this. This is bell curved. I love to do things visually. So what I'm going to do, I'm going to draw a bell curve and put these numbers. I know there's 68% here, 95%, 99%. My mean value in this problem is 3,000 grams, 3 kilograms, right? Then, and the standard deviation is 500 grams. So one standard deviation out of the mean is 3,000 plus 500, right? That's mean plus 1 standard deviation. This point here is 1 mean plus 2 standard deviations, so 3,000 plus 1,000. Here we're going negative. This is the mean minus 1 standard deviation, so mean minus 500. Mean minus 2 standard deviations, so mean minus 1,000. Then I simplify the numbers. These are my numbers. Okay? Doing this only visually. This is awesome. Okay? Now the first question was, what is the distribution of babies, or what percentage of newborn babies weigh between 2,000 and 4,000? Oh, look at that. I got those numbers exactly here. It's like I made up this problem. Okay? So I have 2 kilograms to 4 kilograms. They're within 2 standard deviations out of the mean. So 95% of newborn babies, I can just say that. I can make that statement from the empirical rule. So you could say, because the data is bell-shaped, using the empirical rule, we can infer that 95% of newborn babies weigh between 2 and 4 kilograms. Okay? You can make that statement. Okay? Okay. So now the other question is, what percent of newborn babies weigh less than 3,500 grams or 3.5 kilograms? Okay? So we can do this visually. All right? So I want the percentage of babies that lie below, like all of these, or I want all of this area, all of these points. What's the percentage of the data that lies here? Okay, so if I look at this graph, I know that in this interval, there's 34% of the data is here. But then from here all the way to minus infinity, I have 50% of the data. Why? Because this is a symmetrical graph. This is the median. This is right in the middle. So 50% of the data is to the left, 50 is to the right. So I know there's 50% until here, plus 34%. Well, that gives me 84%. So I know that 84% of babies, of newborn babies, are going to weigh less than or equal to 3.5 kilograms. That makes sense? Visually, doing this visually. Okay. Now you can do it analytically by hand. You take the distance from the mean, 3,500 minus the mean gives you 1 standard deviation. So you're 1 standard deviation out. And then you have to look at the graph. You got 50% until the middle, and then 34%. You add those, and you get 84% of the data. Okay? Yeah, so it shows up like this. All right? 50% of the data here, and then 34% of the data there. And finally, is calculate the range of birth weights that would contain the middle 68% of newborn babies, where we just kind of looked at the graph. We had plus 1 standard deviation and minus 1 standard deviation. That was 2.5 kilos and 3.5 kilograms, right? Because the middle was 3,000. So we go back to this guy. Oops, here, right? So 68% of the data are here by the empirical rule. So that by definition is plus 1 standard deviation out, minus 1 standard deviation. So babies, 2.5 kilograms and 3.5 kilograms. That's like right in the middle of the data. Okay? That's how we use the empirical rule. So that's good. Again, we're doing descriptive statistics. These are numerical description of data. You can say, oh, this much percentage are here, this much percentage is there. There's like however many percentage above 4.5, heavier babies, etc. Okay. Now, what if the data is not distributed as a bell curve? We can't say much, but we can put a lower bound on it. We can say at least this percentage. It could be more, but at least it's this much percentage. That's the best we could do. And this is called Chebyshev's theorem. And it says for general distributions, the proportion of data that lie within k standard deviations of the mean, so this could be plus k or minus k, doesn't matter, then the mean is at least 1 minus 1 over k squared. So what a beautiful formula. So that's a fraction, in percentage is going to give you 20, 30, 40%, okay? So for example, for general data, for general data distribution, k equal to at least 75% of the data lie within 2 standard deviations of the mean. For a bell curve, it was, what, 95%, right? So this theorem does check. For 3 standard deviations, at least 88% or 89% of the data line within 3 standard deviations. So if you don't know what your distribution is, you use Chebyshev's theorem. Or your distribution is not a bell-shaped curve, some weird curve, use Chebyshev's theorem. Gives you at least some estimates. Now, eventually, once we get computing, we can compute the actual areas of those curves and calculate the numbers exactly. But you're flying on an airplane, and they ask for a statistician. For some reason they want to calculate the people's weight on the airplane so the plane doesn't tip one side or the other, and you draw a distribution, right? Some back of the envelope calculations, you use this stuff. Okay, very powerful. You're listening into a survey on the TV, and you're like, let me think about this, right? And then you throw in a statistic, and everybody is going to be like, wow, you're so smart, right? So use this stuff. Okay, applying Chebyshev's theorem. Let's go through this example real quick. In April 2019, the average rent for an apartment in San Francisco was reported to be $3,600. Suppose that the standard deviation of the rent prices is $540. What percentage of rent prices are between 1989 and $5,000? Can you imagine paying $5,200 in rent? Probably a crappy studio in San Francisco. Yeah, we rented a little studio in Los Angeles once. It cost us almost like we had to sell a kidney just to pay for that. It's insane. Okay, so we don't know what the data distribution is here, so we need to figure out, we need to use Chebyshev's theorem. Now, to use Chebyshev's theorem, we need to know how many standard deviations we are away from the mean with these data points, okay? With these data points. And again, Chebyshev's theorem tells you 1 minus 1 over k squared. So once you know k, or your standard deviations, your standard deviation from the mean, then you can estimate what percentage it is. Now, this number could be minus 1 standard deviation. This could be plus 3 standard deviations. You get the percentage for each area, and you add them up together, okay? So in this case, they just happen to be equal to each other. So distance from the mean is minus 3 for the lower rent. Distance from the mean is minus 3 standard deviations. And for the higher end rent is 3 standard deviations. So k equals 3 exactly here. And then you can use Chebyshev's theorem, 1 minus 1 over k squared, which gives you 89% of the data lie. 89% of rents are in this range, okay? 89% of rent prices lie in this range. All right. Now, like we did for the mean value, where we had to do something different when we had frequency distributions. Remember when we talked about the mean value, when we were talking about the mean value, we said it's easy to compute the mean value if you have all the data, whether population or a sample. You sum up the data, divide by the number of data points, and you're done. But what if you were given a frequency distribution? You're not given the original data, you're only given a frequency distribution. How do you compute the mean? We came up with a strategy. We take the mean value of each bin and multiply that mean value by the frequency, the count in each bin. So that gives us a representative number of data points. And then we average all of those, okay? So there's a similar question that's going to occur for standard deviation of group data. What if you're given group data and you want to calculate the standard deviation, starting with, or the variance? They're the same thing. So there's a formula for that. It's a little complicated, but not that entirely hard to derive. So this will be one of your on one of your homework assignments to derive this formula. But essentially, if you bring in the frequency count, this f sub I, and xi is your center data point for a given bin, you use this formula to compute the variance. Now notice here, the summation is carried out over all your classes. Okay, so you might have 1,000 data points, but 5 bins, right? So you're only summing up over the 5 bins. You take the summation over the 5 bins of the frequency count for each bin times the center value squared for each bin, and minus that's other summation here, and you divide by n minus 1 the total number of data points, which you know by summing up all the frequencies, you know the total number of subjects in your study, in your analysis, right? Now, this is for a sample, And if you are doing it for a population, same thing would apply, but you'd have an n in the denominator, okay? So this is a convenient formula. It's not going to give you the exact variance or standard deviation. So you take the square root to get the standard deviation. But it's very close because you don't have access to the original data. This will get you really, really close. Typically, you know, you're going to do this in like a Google sheet if you're just given the distribution. So you have your bin sizes and you have your frequencies, for example, like I'm showing here. And then what you could do, you just do the class midpoint like we did for the mean value, and you run a total row of totals at the bottom. Then you do that fi times xi, and you sum it all up, fi times xi squared. So you're taking the frequency count multiplying by this, or the frequency count multiplying by this squared, and you just implement that formula, and you get the answer for group data. Okay. So you can work through this. There's another example also here for gas prices. You can work through those. They're also in the textbook as well. Shouldn't be that hard to put them in your Google or do them by hand, okay, or your calculator. I want to get to this last section, which is kind of putting everything together. There's also something called measures of relative position, and that gets us into, oh, you're in the 50th percentile, or you're in the 25th percentile, or the 10th percentile, 90th percentile. You know those rankings, right? So we're going to get into the bottom of this once and for all. You've probably seen this, I don't know, but I have to cover it for due diligence. Okay, I take my job very seriously, so we have to cover this. Okay, now by definition, the pth percentile, so 5th, 6th, 10th, 50th percentile, is the location of the data point, okay, where p% of the data is less than p, and 100 minus p% of the data is above that. So 25th percentile is the location of the data where 25% of the data is below that value and 75% is above it. 10th percentile is 10% of the data is below that value and 90% is above it. When I was applying to the US for my grad studies, I went and took some exams like GRE and a bunch of other stuff. And they gave me these rankings, like this is one like 50th percentile or like 10th percentile. I was like, oh, I'm 10th percentile, that's great. And then, you know, my teacher had to explain that to me. No, that's bad, 10th percentile, you're only better than 10% of the others. So there's 90% of the people doing better than you. And so, you know, these are useful numbers to report in terms of statistics, okay? So for example, 25th percentile is the data value where 25% of observations are below that value and 75% above it. Same thing for the 10th percentile, 1st percentile, 60th percentile, however you like it. Okay, so now how do we find that value in practice? And we're thinking here discretely. You have a set of data, you know, 0.1, 0.2, 0.3, 0.4, etc. You have all of those data. So the trick is to split those data into percentages. Okay, and the math works out really very simply. And you take the total number of data points and multiply by the value for p, which is 25 or 50 or 60 or 10, and divide by 100. Now that calculation is going to give you the location of where that data value is. It's not going to give you the data value, it's going to give you the index of that data value. So essentially the way we do these percentiles is you take an array, you're only looking at the number of entries in the array. So is it 100 entries, 50 entries, 200 entries? Where is the 60th percent entry? You just find the index of that, and from the index you get the value. Okay? So if you think about what we did with Python, you have an array, index 0, 1, 2, 3, etc. All you need is that index to find the percentages of those data. If you have 100 data points, then each data point is 1 percentile. If you had 200 data points, each 2 data points is 1 percentile, right? And that's what this calculation is giving you. It's trying to approximate where that percentile location is, okay? Now, L is the left-hand side is the location of the pth percentile in the ordered array of your data values. So you have to order your values first. P is your percentile, could be 25, could be 10, could be 1. Don't divide it by 100. Don't put 0.25 because you're dividing by 100 anyway here to account for that. So this procedure is very simple. You first convert the data into an ordered array. So you sort it. If you have your data in Google Sheets, go and sort that array, or Python, numpy.sort, and then apply the formula. Now the formula could give you either an integer value or a decimal or a real number with decimal point. If the formula results in a decimal value for L, then the location, the index of where that value is, the actual number, your salary or your height or whatever, is the next larger whole number. So if you get 7.5, then the location of your data point is at location 8. Now interestingly, if the formula results in a whole number for L, then the percentile value is the mean of the value at that at that index plus the one right after it. That's one way we compute percentiles. You will see that if you do it by hand, it's going to be different than Google Sheets. It's going to be different than Excel. Okay, Google Sheets and Excel, they use approximations to these percentiles. Okay, so it's a little different, but either value is going to be just fine. If I ask you to do it by hand, do it by hand. It's going to give you the number that I would want. If I tell you to do it in Google Sheets or Excel, or I don't care exactly what that percentile is, then, and I'll tell you to do it in Google Sheets, you do it there. Okay. Now, there's a couple more definitions, and we'll do an example together, and it will anchor the idea in your mind very, very quickly. Okay. There's a few percentiles that are easy to remember. 25th percentile, 50th percentile, 75th percentile. 25th percentile, we say that, we call that the first quartile of the data, first quarter of the data. This is where the first 25% of the data occurs. Q2, or the second quartile, is 50th percentile. That coincides with what? The median. Yes, the median. That's where half the data lies below that value, half above it, right? And Q3 is the third quarter, or the third quartile, is the 75th percentile, or 75% of the data are below that value and 25% above it. Okay, let's do an example. Measurements of the resiliency modulus in megapascals, MPa, on 18 specimens of recycled concrete aggregate produce these ordered values. 100, so they're doing strength testing on these specimens of concrete, see how you're going to support the structure. They sample randomly from the plant, and they get 136 megapascals, 143, 147, 151, blah, 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 all the way to 205. The question is obtain the quartiles, so Q1, Q2, Q3, and the 10th percentile. So I'll do Q1 and Q2, and then the rest just becomes obvious, okay? So we have 18 data points over here. And by definition, the first quartile, or Q1, is the 25th percentile. So my P is equal 25. Don't do gymnastics in your mind. I thought this was going to be 2.5 or 0.25. 25th percentile, P is 25, period, okay? Then you just simply apply the formula. The location of the data point in that array where the 25th percentile occurs is n times p over 100. That's 18 data points, times 25 over 100 gives you 4.5. But we don't have an index at 4.5. The first entry is at index 1, second entry at index 2, third entry is index 3, index 4, index 5. So what do? We round up. We take the fifth value. So the location of the 25th percentile is the fifth data point. That's what L means. It's the location in the array, in the ordered array. If you think about it, we're only taking a number of items and seeing what percentage is of the data located at index 1, index 2, index 3, index 4. Again, go back to the idea. If you have 100 data points, each point is one percentile. The 10th percentile is data point number 10 exactly. But what if you have 17 data points, 18 data points? Where's the 25th percentile? It occurs at location 5 approximately. So then we say Q1 is equal 158 megapascals. Q1 is not equal 5. Q1 is located at index 5 in the array of data. Okay? Same thing for the 50th percentile, the second quartile. It's P equal 50, L equal NP over 100. You get 9 in integer value. Okay, now the rule tells us you don't just pick 9, although you could pick it, but the rule tells us we pick 9 and 10, the value at index 9 and index 10, and we average them. So it's those two values. 165 is at index 9, 167 is at index 10, and we average those two values. And we say our Q2 is equal to that average, which is 166 megapascals. In other words, 166, in other words, 50% of the data are below 166 megapascals, and the other 50% are above 166 megapascals, okay? And the rest, the other questions, you can just do it yourselves, okay? Now, what is the 0th quartile? The lowest point, the minimum value in the data. The smallest data point, the minimum. What is the 4th quartile? The largest value, the maximum value. Good, okay. Now we can proceed to what we call the 5-number summary and box plot. So this is the cherry on top of the cream of the cake of numerical statistics. With these 5 numbers, these are the 5 numbers you want to use to numerically summarize any set of data, descriptive statistics. Okay, they are Q0, Q1, Q2, Q3, and Q4 we call that the 5-number summary for any data point, for any data set. So essentially the minimum value, maximum value, first quartile, 25% of the data, second quartile, 50% of the data, and third quartile. Now the second quartile, Q2, is the median, right? Which is great, kind of tells us the median about the data. All right. So here's an example. What's going on here? Okay, so this is 3.3.3, example 3.3.3. So let's see that on Google Sheets. All right, so open your Google Sheets, example 3.3.3. So I want the four quartiles for these data. So this is a set of data that's been ordered. It's about mileage driven. There's 133 data points, 132 data points. Okay, so that's the highway mileage data that's been given to us. And I want to find the 5-number summary for those data. Okay, the 5-number summary is Q0, Q1, Q2, Q3, and Q4. Okay, so Q0 is simply equal to, I can take the minimum of the data, or I'm going to do better. I'm going to use the built-in function in Google Sheets to find the quartiles for you, and that's simply quartile. So you type quartile, okay, and you pick the data, and you say, I want the 0th quartile. 12.1, indeed, that's the minimum. Okay, Q1 is going to be the first quartile. I'm going to select the data, and I'm going to put 1. Now, this doesn't give you the percentile, gives you the quartiles. So you can't put 25 over here or 10. These are quartiles, okay? Zeros, first, second, third, and fourth. Okay, that's it. Okay, so you get 19.75. So in other words, 25% of the data lie below 19.9 miles per gallon. Q2 is the second quartile, and then Q3 is the last one. No, not the last one, sorry. That's where 75% of the data, and the last one, Q4, is the maximum value. I'm going to put 4, and indeed gives me 35.9. If I go down, that's the maximum value, 35.9. Okay, and we are out of time. It's unfortunate, but we will pick up from here on Thursday. Okay, and we'll do what's called the box plot. Okay, thank you, Godspeed.